There we go. All right, can everybody see my screen? I just want to make sure that everybody can see it before I start yammering on here, talking about chapter 13. Okay, great, wonderful. So this is Chemistry 1401. This is chapter 13, Properties of Mixtures, Solutions, and Colloids. We're going to spend most of the time talking about solutions. That covers the majority of the chapter, and we talk about colloids a little bit, just a little bit. But before we get into the real nitty gritty, we need to talk about definitions of concentration. And the thing is that we did use some of these definitions. For example, we used molarity earlier on when we looked at stoichiometry earlier on in this class. So concentration definitions, let's go through them all here. The first one is molarity. So you might remember that molarity, I used a formula that looked like this. So I would use big M is equal to N over V, which is molarity, or the number of moles per liter, is equal to the number of moles of a substance divided by the volume in liters. And note that it's the amount of solute, so the number of moles of the solute divided by the liters of the solution. So the entire solution has to be taken into account there. Now, the next one is molality. And for molality, we use a little m. And if you've never heard of molality before, you might even think it's kind of a weird word. Well, what molality is, it's got the same numerator as molarity. However, the denominator is different. So it's the number of moles of solute divided by the mass of the solvent in kilograms. In fact, if you look at all of these different concentration terms that are on this page, molality is the only one where you divide by the mass of solvent only. Okay, you see it, the others all involve solutions. So solute plus solvent is a solution. Anyhow, so that's something that's special about molality. Now you might be wondering, like, why would I want to, have this concentration term, molality? Why would I want to divide the moles of a solute divided by the mass of a solvent? What's so great about the mass of a solvent? Well, there's a couple advantages to using molality, and we use molality in specific situations. And they have to do with, or the advantages have to do with the fact that when you're measuring molarity, you're dividing by the volume of a solution. Well, the problem with dividing by the volume of a solution is twofold. The first thing is that we know that density of a liquid is going to depend on temperature. So the molarity of a solution is going to be temperature dependent. So if we're, looking at our solution at different temperatures, well, then its molarity changes. Whereas mass doesn't change, right? Volume does change with temperature, but mass doesn't change with temperature. So that's the first reason. And the second reason is that masses are additive. What do I mean by that? Well, if I add, some different solvents together, let's say I add 500 grams of a solvent, and 500 grams of another solvent. Okay, that's going to equal 1,000 grams. Pretty easy, right? Well, if I have 500 milliliters of one solution and I add it to 500 milliliters of another solution, it may or it may not be equal to 1,000 milliliters. It might be less and it might be more. And you might be wondering, well, why would that be? Well, that has to do with the way that the liquids interact with each other. Okay, so we can have a change in volume there. So based off of those two reasons, you can see why molality would have, its place in chemistry, why it has advantages. The next ones are parts by mass and parts by volume. The first one, parts by mass, is the mass of solute divided by mass of solution. We oftentimes call this percent, W over W. Okay, so this is weight over weight. So it's the mass over mass, which is more correct. It's not the weight over weight, but that's the representation you'll see if you look at, a packaging or something that has percent by mass on it. Okay, and for percent by volume, that's going to be percent V over V, a little more intuitive. So the volume of solute divided by volume of solution. And then finally, the last one is mole fraction. And that's something that we looked at earlier on. We looked at mole fraction back in chapter 5. So it was section 5.5 when we looked at Dalton's laws of partial pressures. We learned that mole fraction is equal to the amount of moles of a substance. So here it's saying solute divided by the total number of moles. So solute plus solvent. You have to be familiar with all of these, and you have to be able to work out problems that deal with these. Okay. And before we get into some problems, let's look at a couple more definitions here of concentration terms. Parts per million and parts per billion. If you are the kind of person who drinks bottled water, maybe you've looked at the label on bottled water and you'd say, well, shouldn't bottled water be mostly water? Yeah, it is, but you'll see that there's tiny amounts of different minerals in there, like maybe magnesium or calcium. And the thing is that the concentration of those ions is so low that they are reported in parts per million or parts per billion. So parts per million, this is ppm, so ppm, and parts per billion, this is ppb. Now, parts per million and parts per billion are just the mass of solute divided by mass of solution multiplied by either a million, 10 to the power of 6, or a billion, 10 to the power of 9. Now, you might be wondering, why would I want to have, ppm and ppb? What's so good about that? Well, the reason why ppm and ppb are useful is because if you're looking at something that's extremely dilute, you don't want your concentration and molarity to be 0.0000. You lose track of zeros, right? So it might be handier to express it in ppm or ppb. Okay, now something that's important to note before we move on and we tackle a question that involves ppm or ppb is that the units of mass have to be the exact same. Okay, for example, if I have grams of solute, I've got to have grams of solution. If I have milligrams of solvent, I've got to have milligrams of solution. If I have kilograms of solvent, I've got to have kilograms of solution, like that. Okay, so the masses have to be written in the same units on these equations. All right, well, let's move on from there. Let's look at sample problem 13.1. What is the molality? Remember that molality was little m, and it was the number of moles of solute divided by kilograms of solvent. Okay, so we want to keep that in mind. Remember, it's kilograms of solvent only. What's the molality of a solution prepared by dissolving 32 grams of calcium chloride in 271 grams of water? Now, I've already gone ahead and written it here, but it's saying here that in our plan that molality is defined as moles of solute divided by kilograms of solvent. All right, well, let's go over here where we've got a little bit more space, and let's see if we can solve this problem. This would be a perfectly legitimate problem for the final exam. What's the molality of this solution? Well, remember, again, that molality, oops, I'm going to need a pen here. Molality, little m, is equal to the moles of solute divided by kilograms of solvent. Well, first we need to figure out the number of moles of solute. And what would our solute be here? Our solute would be the calcium chloride. Okay, so our solute is our calcium chloride. Now I've gone ahead and I've looked up the molar mass of calcium chloride. It is, what did I write down here? 110.98 grams per mole. So we can work out the number of moles in the numerator, can't we? We could just say 32.0 grams of calcium chloride divided by 110.98 grams of calcium chloride in 1 mole of calcium chloride. So I have all that in my numerator. You can see that grams and grams cancel, and I'm left over with moles. And then kilograms of solvent, well, they've given me the mass of the water in grams, but we know that there's 1,000 grams in a kilogram. So let's do all that math in the denominator. So we'll put here 271 grams. And what do we got here? We got 1,000 grams in 1 kilogram. Again, you can see that the units of grams cancel like that. And when we work all that spinach out, we get 1.06, so 1.06 molal. So that's how we say that. We say that molal, okay? Molal calcium chloride. What do you think? Perfectly legitimate problem. Who thinks they could solve that problem on the final exam if they were faced with a problem like that? Give me a thumbs up if you think you could tackle that one. Great, thanks, Brittany. Okay, perfect. So what you really need to memorize is this equation right here, okay? We'll put that in here, memorize the equation for determining molality of a solution. All right, well, let's look at some more problems. So this is the solution put forth by the author of the textbook. Anyhow, let's try some other ones here. I got 3 different problems. Let's give them all the old college try. Let's see. Let's just start with the first one and we'll backtrack if we have to. So we're just going to look at A. It says find the concentration of calcium in ppm of in a 3.50 gram pill that contains 40.5 milligrams of calcium. So we're looking for the concentration of calcium in ppm. Well, let's go ahead here and let's write down how we define ppm. And the way we do that is that parts per million is equal to the mass of solute divided by mass of solution. And if you're thinking like, well, where's the water? You know, I don't have any water here. This is a solution of a solid calcium in a solid pill. So this is a solid solution. Anyhow, and then we're going to take that and we're going to multiply that by 10 to the power of 6, right? A million. Now, again, it's important that the units are the same. I've got 2 different types of units here. I've got milligrams and I've got grams. I'm going to choose to put everything in grams, just because. And if you want to put everything in milligrams, no problem. You'll get the same answer. So we're going to have the mass of the calcium, the solute, in grams, and we're going to have the mass of the solution in grams. Well, let's start plugging in some numbers. My ppm, my parts per million, mass of solute in grams. So we have 40.5 milligrams. And I know that in 1 gram, I have 1,000 milligrams. So I'm going to put that in my numerator, and the mass of my solution, I already have that, 3.50 grams, like that. All right, so milligrams cancel. And when I punch all that, oops, I forgot my times 10 to the power of 6. Let's plug that in here, times 10 to the power of 6. When we do that, let me get my calculator out here. So I have 40.5 divided by 1,000. Could have done that in my head. Divided by 3.5 times 10 to the power of 6. And convert that into scientific notation. I get 1 point. How many sig figs should I have? 1.16. 1.16 times 10 to the 4 parts per million, like that. 1.16 times 10 to the 4 parts per million of calcium. All right, there we go. And so again, this is another example of where you're going to have to memorize a formula. There we go, parts per million. All right, let's keep moving. Let's try another problem. This is B. It says the label on a 0.750 bottle of Italian Chianti measures 11.5% alcohol by volume. How many liters of alcohol does the wine contain? Well, you'll remember that if it's 11.5% alcohol by volume, what does this by volume mean? Well, we already looked at that and we said that percent volume, okay, is equal to the volume of the solute divided by the volume of the solution. Okay, like that. And then, of course, since it's a percent, we're going to multiply that by 100%. Okay, now if our percentage is 11.5%, we're trying to figure out alcohol is dissolved in the wine, right? Keep in mind that the numerator, the solute, this is the alcohol, pure alcohol, and this is the wine. That's the Chianti, the entire thing. So we have 11.5 is equal to X, the volume of our solute, divided by the volume of the solution was what? 0.750 liters. Multiply that whole thing by 100%, like that. When we work that out, we get the X is equal to the volume of our solute, which is the alcohol in this case. And just let me double check here. So I have 11.5 divided by 100. And I get 0.0. How many sig figs should I have here? 863 liters. There we go. So there's the final answer, just like that. Okay, 0.0863 liters. And again, memorize this formula. You're going to have to know how to calculate this. But remember, if you're overwhelmed with all these formulas and saying, well, you know, it's a lot of formulas, remember, percent volume is just going to be volume over volume multiplied by 100. But remember, all of these formulas that we're looking at, it's always solute divided by solution, right? Always solute divided by solution, except for molality, right? So you only really have to remember one, where it's solvent, moles of solute rather, divided by moles of solvent, okay? Only one. All right, that has solvent in the denominator. Okay, let's try the last one. See, did I give myself enough room to solve that? No, that would be too easy. Okay, so let me make a little room here. While I'm doing that, you can take a look at the problem, start tackling it. I make myself a little space here. All right, so this was B, and this is C. There we go. Okay, a sample of rubbing alcohol contains 142 grams of isopropyl alcohol. It gave us the formula, and 58 grams of water. Everybody knows the formula of water. What are the mole fractions of alcohol and water? Well, remember that mole fraction, excuse me, which we expressed as X before, is equal to the number of moles. Oops. Let's just do it easy. Let's just, why don't we just calculate the number of moles of isopropyl alcohol and water first? So let's figure out the number of moles. So number of moles of C3H7OH is going to be equal to 142 grams divided by, and I've looked up the molar mass of isopropyl alcohol. It is 60.09 grams per mole. Okay, so 60.09 grams per mole. When I work all that out in my calculator, let's see, that's equal to 2.36 moles of isopropanol, so C3H7OH, like that. Now we want to figure out the number of moles of H2O. I'm sure many people who are watching this video or who in class right now have the molar mass of water memorized, 18.02 grams per mole. Okay, we see that grams cancel. We're left over with the number of moles of water, and we get 3.22 moles, like that, of H2O. So if we add these two together, okay, we add them together, we get N total, which is the total number of moles. So 2.36, excuse me, 2.36 plus 3.22, and we get 5.58 moles. So that means that the mole fraction of C3H7OH, so isopropanol, is 2.36 moles divided by 5.58 moles. And that's going to be 2.36 divided by 5.58, which gives us 0.423. 0.423. So that's the mole fraction of isopropanol. Mole fraction of water. I mean, we could just take 1 and subtract 0.423, but where's the fun in that? So we'll do 3.22 moles divided by the total number of moles. I find it hard to write in the bottom corner of this tablet. There we go. So 5.58 moles, like that. 3.22 divided by 5.58, 0.577. So 0.577. And there we go. We've got the mole fraction of our isopropanol or isopropyl alcohol and the mole fraction of our water. And we can check this one, right? We can add these two numbers together. So if I take 0.577 and I add 0.423, I add them together, you get 1. So there you go. It must be the correct answer. Okay, so mole fraction. You've got to be able to calculate mole fraction. Okay, so again, and where I was going at the very beginning, and I kind of stopped myself, was saying, okay, well, if you want to find the mole fraction of I, it's going to be equal to the number of moles of I divided by the total number of moles. Okay, so mole fraction, and again, that's something that we looked at earlier on in the class. Well, let's move on Here are the solutions worked out by the author. Anyhow, let's talk more about interconverting those concentration terms like molality, molarity, percent mass over mass, percent volume over volume. It says to convert a term based on amount, number of moles, to one based on mass, you're going to need the molar mass, right? So that makes sense, right? Because moles are obviously in moles, and then you have mass in grams, and molar mass is in grams per mole. So that makes sense. To convert a term based on mass to one based on volume, you're going to need density. Well, that makes sense because mass will be in grams, volume would be in, let's say, milliliters, for example. And density is usually expressed as grams per milliliter for liquids and solids. Molality involves the quantity of solvent, okay, whereas the other concentration terms involve quantity of solution. I can't, remind you of this enough, okay? Everybody in this class can divide two numbers, right? There's nobody in this class who can't divide two numbers perfectly with a calculator, okay? Now, remembering that molality, involves quantity of solvent rather than solution, that's a key, okay? You really want to keep that in mind moving forward in doing your problem solving in this class. Okay, let's try a problem then. This is kind of a 3-for-1, 3 parts. It says a solution of hydrogen peroxide is 30% by mass and has a density of 1.11 grams per milliliter. Calculate the molality, mole fraction of hydrogen peroxide, and the molarity. So we're going to do all 3 of these. Let's start by working out the molality. Okay, so if it's 30% by mass, okay, if the solution is 30% by mass, that's a way of saying, the percent mass over mass is equal to the mass of H2O2 divided by the mass of solution. Now, if it's 30%, we could just choose numbers, right? We could say 30, I always forget to multiply by 100%, okay? Now, I could just choose numbers here arbitrarily, and I'm going to say, okay, well, if it's going to be 30%, I could say I'm going to have 30 grams of hydrogen peroxide, right, H2O2, in 100 grams of solution. Okay, well, from that, we can calculate the molality pretty quickly, can't we? Right? Because we have 30 grams of our solute, right? This is our solute. But our solution, if it's 100 grams, that's solute plus solvent, isn't it? So if we only want the solvent, the mass of the solvent, we're going to say mass of solvent is going to be equal to 100 grams, subtract 30 grams. I had an extra 0 there. All right, so that's going to give us 70 grams of our solute. Sorry, our solvent. So now we have, look carefully, remember that to calculate molality, we need moles of solute divided by mass of solvent. Okay, if we have the number of grams of solute and we know its formula, well, we can calculate the number of moles, no problem. And now we have the mass of the solvent. So let's set it up. Let's do it. Molality, small m, is going to be equal to 30.0 grams. I'm going to calculate the number of moles of hydrogen peroxide in the numerator. I've gone ahead and calculated the molar mass of hydrogen peroxide, which is 34.0 grams per mole. Okay, so 34 grams per mole of H2O2. So we'll put that in the numerator. And then we have the mass of our solvent. And remember that we want the mass of that solvent in kilograms. Okay, if you back up, and I don't know if I mentioned that a second time, but I'll show you here quickly. If we go back here, or is it here? It's the mass of solvent in kilograms. So I just want to reiterate that. Okay. Where am I? Here we go. Okay, so the mass of the solvent in kilograms. And so if we have 70 grams of solvent, we want to convert that to kilograms. We're going to have 70.0 grams divided by 1,000 grams per kilogram. Look at this, it's a beautiful thing. You can see the units of grams cancel. We're left out with moles on top, and grams cancel, and we're left over with kilograms on the bottom. That reduces to 0.882 moles divided by 0.0700 kilograms. When I divide that, I get 12.6 molal H2O2. And there you have it. That's the molality of my solution, of my 30% by mass hydrogen peroxide. I also want to go back and point out one thing that I should have mentioned here. Parts by mass is sometimes expressed as W over W. That's more of an older way of doing it. Nowadays, we usually use percent M over M. So that's why I wrote percent M over M like that. All right, and there's the solution worked out by the textbook author. Let's go back here. We get some more room here, and let's figure out the mole fraction of hydrogen peroxide. Well, we already know the number of moles of hydrogen peroxide. I'm going to go a little bit quicker here in B. We know the number of moles of H2O2 because I worked it out in the last problem. It was 0.882 moles of H2O2. And I know that my solvent, which is water, because this is an aqueous solution of hydrogen peroxide, I know that I've got 70 grams of water. So remember that my solution is made of hydrogen peroxide and water. And if I want to figure out the number of moles of water, it's going to be equal to 70.0 grams divided by 18.02 grams per mole, like that. Grams cancel, and I end up with the number of moles of water as being 3.88 moles of H2O, like that. So now I have the number of moles of solute, and I have the number of moles of my solvent. And if I want to figure out the mole fraction of H2O2, the mole fraction of H2O2 is going to be equal to the number of moles of H2O2 divided by the total number of moles. So number of moles of H2O2 is 0.882 moles divided by 0.882 moles plus 3.88 moles, like that. Okay, I take all that, 0.882 divided by 0.882 plus 3.88, and I get that the mole fraction is 0.185, 0.185. And it's a unitless number, okay, but that is equal to my mole fraction of hydrogen peroxide. Okay, so now we figured out the molality of the solution, and we figured out the mole fraction of the solution. Well, let's skip ahead to the last part, and let's take a look at molarity. How would I calculate the molarity of this solution? Okay, well, I know the number of moles of my H2O2. Now I need the volume of my solution. Okay, well, we know that molarity, so big M, is equal to the number of moles solute, okay, divided by the volume of the solution in liters. I've already got the number of moles of my solute, don't I? It was 0.882 moles of hydrogen peroxide. Okay, we already got that part done. Okay, no problem. Now, if I want to get the volume of my solution, now I had, if it's 30% by mass, right? Remember that we said that we had 30.0 grams of H2O2 in 100.0 grams of solution, right? That was how we expressed mass over mass, right? Percent by mass. Okay. Well, if I know that I've got 100 grams of solution, and I also know that the solution has a density of 1.11 grams per milliliter, I can figure out the number of milliliters of that solution. Right? All I'm going to have to do is take 100.0 grams and divide it by 1.11 grams per milliliter. And I end up with the volume of solution, which is 90.1 milliliters. Now I can convert that into liters, right? Because I know that 90.1 milliliters, I know that in 1 liter, I have 1,000 milliliters. So that gives me the volume of my solution as being 0.0901 liters, like that. 0.0901 liters. So I've plugged that number in here. And now I'm going to calculate the molarity, which is 9.79 molar. And there we go. We were able to calculate the molality of the solution, the mole fraction of hydrogen peroxide, and the molarity of the solution just from the percent by mass and the density of the solution as well. All right. Give me a thumbs up if you think you could solve those problems, maybe with a little practice. I wouldn't expect you to be able to figure out everything just by hearing the sound of my voice. No, it takes practice in chemistry. Okay, great. Wonderful. Well, let's move on from there and let's switch gears a little bit. And these are all the solutions from the author. And let's talk about solutions in colloids. And you're already familiar with solutions to some degree, right? We see solutions everywhere in our day-to-day lives. A solution is a homogeneous mixture and exists as a single phase. The particles in a solution are individual atoms, ions, or small molecules, but it's homogeneous, right? It's one phase. For example, if you have, a solution of Kool-Aid in water, well, you can't see the Kool-Aid crystals, right? Can you? You know that you put a solid in the water, but then the solid kind of it disappears, right? And you just have one phase. Okay, so that's a solution. It's homogeneous. Whereas a colloid is heterogeneous. It's a heterogeneous mixture and exists as two or more phases, which may be physically distinct. The particles in a colloid are typically macromolecules or aggregations of small molecules. The particles have sizes between 1 to 1,000 nanometers. Now, colloids, for example, are things that are like milky or muddy or soapy water. And why we get a colloid is because the solute particles are larger than simple molecules, but they're too small to settle out, right? They don't just settle out at the bottom. The particles in a colloid are smaller than those in a suspension, but larger than those in a solution. So they're kind of in this, area in between, this size here. So particles that are in a solution are going to be smaller than 1 nanometer typically, and particles in a suspension are going to be typically greater than 1,000 nanometers. Well, how would I be able to distinguish between a solution and a colloid if the particles, macromolecules or aggregations, aren't settling out in my colloid? And the answer is you would differentiate between a solution and a colloid using what's called the Tyndall effect, which was discovered by John Tyndall. And the way that you distinguish between a colloid and a solution is that you shine a beam of light through the solution or the colloid, and you get a different effect depending on whether you have a solution or a colloid. If we look at the figure on the left-hand side, it says the narrow, barely visible light beam that passes through a solution. This is a solution right here. Is scattered and broadened by passing through a colloid. And so that is how you tell the difference. You see how this is looks kind of foggy when you shine a light through it? The reason why is because those dispersed particles in the colloid have sizes that are similar to the wavelengths of visible light. What are the wavelengths of visible light? What we can see with the naked eye. They're around 450 to 750 nanometers, right? And I said that the particles in a colloid were between 1 and 1,000 nanometers. And so that light scatters and it produces that Tyndall effect. Another example, and maybe a more common example of the Tyndall effect, is what we see in figure B, where we see sunlight being scattered by the dust in the air. And again, since it's being dispersed by the particles of dust that are in the air, you see how the beam of light is actually getting bigger, right? It's getting bigger as it hits more particles and is scattered more and more. That is the Tyndall effect. And that's how we differentiate, again, between a solution and a colloid. Let's talk a little bit more about solutes and solvents for a second. A solute is what dissolves in a solvent to form a solution. Now, usually the solvent is the most abundant component in our solution. For example, if we go back to Kool-Aid, right? If you're making a pitcher of Kool-Aid, it's got a lot more water in it than it does Kool-Aid crystals, okay? Now, there is an exception to this. Again, normally we say that the solute is present in a smaller amount. An exception to this is that whenever water is present in a solution, it's always considered the solvent, regardless of it being more abundant or not. Say, for example, you have a mixture of acetone, and acetone can be purchased at Home Depot in the paint section. It can be used as a paint thinner. If you have a solution of acetone and water, and let's say it's 900 milliliters of acetone and only 100 milliliters of water, since water is present, we would still say that water is the solvent. Okay, that's again an exception. Now, the solubility of a solvent is the maximum amount of solute, that maximum amount that dissolves in a fixed quantity of solvent at a specific temperature. Now, you might be wondering, do I have to memorize that, or can I look that up? And the answer is no and yes. You don't have to memorize solubilities, but yes, they can be looked up. Okay. For example, if we were talking about the solubility of sodium chloride. Okay. Now, these are just a couple that I went ahead and researched before the lecture. If we look up the solubility of sodium chloride, what they say is NaCl. They say S, which is solubility, is equal to 39.12 grams per 100 milliliters of water of H2O. And then it even gives you the temperature, and it says here at 100 degrees Celsius. Okay, so very specific. Now, I looked up another one, and the one that I chose was silver chloride. And silver chloride has a solubility of, look at this, 0.0029 grams per 100 milliliters at 100 degrees Celsius. Now, again, solubility, we can actually look up values, numerical values for solubility, but we can also use solubility qualitatively, right? If we were to compare the solubility of sodium chloride and silver chloride, we would just say, okay, well, sodium chloride is more soluble than silver chloride, and we would say silver chloride is less soluble in water than sodium chloride. Now, why do we get solutions, right? We're going to really get into the nitty-gritty of why do solutions even form, right? Why can I mix, sodium chloride in water and get a beautiful solution? Why can I take sugar and dissolve it in water and get a solution? How come I can't mix oil and water, right? We know that they're not miscible. We know they're not mixable, right? But why is that? There's got to be a reason for that. And the reason why is substances that exhibit similar types of intermolecular forces, or IMFs, are going to dissolve in each other. We express this by saying like dissolves like. So if you have two components, solvent and solute, they have similar intermolecular forces, normally they will dissolve in one another. Let's take a look at some examples of intermolecular forces in solutions. Okay, we have 6 different types of intermolecular forces that we would see in solutions, and they're ranked in order of the strength of these intermolecular forces. Well, the first one is an ion and a dipole. All right, we've talked about the structure of water enough times in this class to know, or for you to know, that water is kind of a two-faced molecule, isn't it? Right? It's got a face that's delta minus, and then it has another face that's delta plus. So if we have an ion, and again, they've shown here a cation, doesn't matter, could be an anion. The dipole in water is either going to align its negative face with a cation, as is shown here, or it will align its positive face with an anion, as I'm kind of demonstrating here. Right? I have the chloride near the delta minuses. And that's a really strong interaction between that permanent dipole in water and the permanent charge on an ion. Now, if we progress from there, we see the next one is a hydrogen bond, which is also pretty strong. It goes from 10 to 40 kilojoules per mole. In order to have hydrogen bonding, what are the requirements? You should know this. You either have to have a bond between oxygen and hydrogen, nitrogen and hydrogen, or fluorine and hydrogen. Here they're showing methanol and water. Now, in methanol, we have an oxygen-hydrogen bond, and in water, we have two oxygen-hydrogen bonds. And so we have the delta plus. What they're showing here, this is the hydrogen of a methanol molecule, hydrogen bonding to the lone pair on the oxygen. So you should be able to represent hydrogen bonding. The way I put it to my students is this. Anybody who's in this class should be able to go to a student who's in a lower level chemistry class and explain hydrogen bonding to them. Okay, well, what's next? We have dipole-dipole. In the example that's shown here, two different molecules, but they both have a dipole, don't they? I have ethanal, and if I draw the Lewis structure of ethanal, it looks like this. I'm not going to have the time to draw the Lewis structure of every single thing. Okay, but you can see that there's a dipole in ethanal, isn't there? Because we have a polar bond, right? The carbon-oxygen bond is a polar bond. Remember, and I'm just kind of going off to the side here, carbon-hydrogen bonds and carbon-carbon bonds, okay, not polar. Okay, those are not polar bonds. So that's why I only highlighted that bond, because that's a polar bond. If I look at the structure of chloroform, CHCl3, so CHCl3, and I'll draw, the VSEPR structure like this, and I'm not going to reteach VSEPR at the moment, but chloroform is a polar molecule too. So since these two molecules both have those red arrows, right? They both have permanent dipoles. The delta plus of one of those molecules is going to be able to interact with the delta minus of the other molecule, and that's what they're showing here. This is the delta minus on the oxygen interacting with the delta plus by the hydrogen on chloroform. So we have a dipole-dipole, and that's why ethanal will be soluble in chloroform. I'm sure many of you haven't even heard of ethanal. Common name, which is acetaldehyde. It's one of the chemicals that's responsible for a hangover. Anyhow, that's another lecture. The next one is an ion and induced dipole. Remember that in an induced dipole, that's what Mr. Dion calls a London force. Okay, a London force is the same thing as an induced dipole. Okay, so London forces. And here we have an ion, a chloride, for example, which has a permanent charge, doesn't it? Okay, well, here it's showing it interacting with hexane. Now, you can see the numbers are getting lower here, and the solubility is going to be more limited here because there isn't a permanent dipole in hexane, right? It only has London forces. So what if, they're showing you the positive, they're showing the dipole arrow, and they're saying, okay, well, what if at a moment in time, most of the electrons in the electron cloud are over on this face of the molecule? That's going to render this face delta positive, and then we're going to have that interaction. But again, it's going to be weak because that dipole shown here in the hexane, that's not permanent, right? That's fleeting. That's induced, okay? The next one is an induced, a dipole and an induced dipole. For example, how soluble is xenon, which is a noble gas, in water? Well, xenon has an electron cloud, and if you look at the noble gases, xenon is down in the 5th period, so it's actually pretty big, okay? And so remember that an induced dipole, the more polarizable the molecule becomes, and if you're wondering what's polarizability, well, I went over it before, but polarizability is basically the ability of the molecule to distort its electron cloud. So the bigger the molecule it is, the more polarizable it becomes, and the better able it will be able to interact with the dipole, okay, or ion in these these two examples here, okay. So again, what's going on here? Well, in xenon, what if all the electron density, lines up on one side of the molecule? Well, that's going to render this side delta plus, and then I can have an dipole, induced dipole. Okay, and remember, it's saying induced dipole, right? So what does induced mean? It means that once the xenon or the hexane approaches something that's already got a charge or a partial charge, right, that's going to repel you know, the negative charge on the chloride is going to repel these electrons, so it's going to create the induced dipole. And a similar effect here, right? We have the delta minus on the oxygen, so that's going to repel, you know, the electrons that are around the xenon, okay, like that. And then the last one is the Lowly dispersion force, but there's a reason why octane and this molecule here, this is called hexane. There's a reason why these two hydrocarbons are soluble, right? There's a reason why you can dissolve hexane and octane together. It's because they both only have dispersion forces, right? London forces. And again, we follow that rule of like dissolves like. Now, one thing you'll notice about this slide, okay, is that except for, you know, these numbers that you see here, which is just, you know, kind of ranking these in order of their strengths, this is a largely conceptual slide, isn't it? Okay, there's not a whole lot of the answer is, you know, equals 6, right? It's more, do you understand what is going on here? So I think we would be remiss, you know, to not look at some problems that deal with types of intermolecular forces. But before we do that, I want to talk about a few more things, okay? So just give me a little bit more time, and I promise we'll look at some questions that involve, you know, evaluating intermolecular forces and solubility. When a solution forms, the solute-solute attractions and solvent-solvent attractions are replaced by solute-solvent attractions. Now, the only way that this can occur is if the forces within the solute and the solvent are similar to the forces that replace them. Right? Think about it. If we have a solute, okay, well, there's some kind of intermolecular force holding the solute together. And then I have a solvent, there's some kind of intermolecular force holding that together. Why would it make a solution unless the interactions between the solute and the solvent were similar, were favorable? Okay, so that's the kind of thing that we want to keep in mind moving forward. Here is a picture showing what's called a hydration shell around a sodium ion. If we go back to that solubility of sodium chloride in water at 100 degrees Celsius, we said it was 39.12 grams in 100 milliliters. That means it's around 390 grams in a liter of boiling water. That's a lot of sodium chloride. Why would sodium chloride be so soluble in water? If you've ever dissolved salt in water, you know it's pretty soluble, right? There's a reason for that. Okay? And it's because the water forms what's called a hydration shell around the sodium ion and around the chloride ion as well. It stabilizes it, right? It's got to stabilize it. So the ionic forces that were present in the sodium chloride are replaced by similar forces. It's not an ion-ion force, but it's an ion dipole, right? And you know that the oxygen, and that's where the oxygen is here in the water, right? This has a delta minus, delta minus, delta minus, delta minus, right? So it's forming this shell. Where's my other delta minus here? Now, in sodium, if this was a sodium cation, sodium can have 6 water molecules surrounding it in an octahedral arrangement. Lithium, if you look at the periodic table, has a principal quantum number of 2 and is therefore a smaller ion. Okay, and we're going to look at hydration a little bit later on, and we're going to talk about it even from a quantitative viewpoint. Well, what about dual polarity and effects on solubility? For example, if you look at an alcohol, and we looked at methanol earlier on, alcohols are organic compounds. That's compounds that contain carbon, and they have a dual polarity. And if you're like, well, what do you mean by dual polarity? What I mean by that is that an alcohol has a polar region, and it also has a nonpolar region. Okay, the generic formula for an alcohol is shown right here. Okay, CH3, CH2 in brackets, N, where N can be 1, 2, N can be 0, 1, 2, 3, so on and so forth. Well, let's take a couple of different alcohols here. If I have CH3OH, that's called methanol. Okay, if I have CH3, 1, 2, 3, 4, 5, 6, 7. Okay, this is called octanol. Octanol, right? Octanol. And you can guess where the oct comes from, right? I got 1, 2, 3, 4, 5, 6, 7, 8 carbons. Okay, I want to double check that. Okay, so octanol and methanol. They both have the same generic formula, right? They both have a hydrocarbon portion. Hydrocarbon means made made of only carbon and hydrogen. I'm circling or boxing them in yellow. Okay, these parts are non-polar, right? Why? Because I told you that carbon hydrogen and carbon bonds are not polar. So this is non-polar, this is non-polar. And then you're like, well, hold on, Mr. Dion, hold the phone. Here I have an OH bond and here I have an OH bond. That's polar, right? And you're right, that's really polar, right? That's capable of hydrogen bonding. Okay, so again, if all alcohols have this generic formula, then they all have a polar part and a non-polar part. Okay, that polar part, that OH group of the OH group of the alcohol, it's called a hydroxyl, and you have the OH group of the alcohol is polar. It can interact with water through what? Hydrogen. Okay, but how would that OH group interact with a molecule like hexane? Now keep in mind that hexane is CH3, CH2, 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 CH3. So that's hexane, okay? So completely non-polar, right? Only carbon-carbon and carbon-hydrogen bonds. How would it interact with the OH? Through dipole and induced dipole forces. Those are much weaker than hydrogen bonds, aren't they? Okay, so you got to be able to evaluate these things in your mind. Now, what about the hydrocarbon tail? Right, the hydrocarbon tail we said was non-polar. So what kind of intermolecular forces is that going to experience with water? It's going to have a dipole from the OH and an induced dipole force. That's weak, right? And it's going to interact through dispersion forces with hexane, right? Remember, like dissolves like. Okay, so if I tally up everything that's occurring on this slide here, all the wording on this slide, what does it mean? Okay, it simply means this. If you take a small alcohol, okay, an alcohol that's got a little tiny hydrocarbon group on it, that's going to be much more soluble in something like water than octanol will be. In fact, octanol doesn't dissolve in water at all. Why? Because even though it's got a portion, it does have that OH on it, which can hydrogen bond. I'm not taking it away from it. It can do that. But hold the phone. I mean, the hydrocarbon portion is just so darn big that it negates any of that hydrogen bonding. Okay, it doesn't hydrogen bond enough, or the hydrogen bond isn't strong enough to pull that big non-polar tail into solution. If you want to look at it in graphical form here, or in tabular form, remember that an alcohol has the generic formula CH3, CH2, and OH. As we go from n is equal to 0 to n is equal to 1 to n is equal to 2 to n is equal to 3 to n is equal to 4 to n is equal to 5, right? As we increase the size of the nonpolar portion, what's going to happen to its solubility in water? Look at the first three. Infinitely soluble in water. Infinitely soluble in water, there's a way that we can describe that in one word, and that's called miscible. It means mixable in all proportions. But look what happens once you get up to n is equal to 3, 4, and 5. Right? You see that the solubility in water decreases. Why? Because the hydrocarbon portion, this portion, is getting bigger and bigger and bigger, right? And the hydrogen bonds just aren't strong enough to overcome all of the nonpolar portion, which is not soluble or is insoluble in water. Now, if we look at the opposite, if we look at the solubility in hexane, which I'll just put the molecular formula is C6H14, so completely nonpolar, you see that methanol doesn't dissolve in solubility very well. It has a low solubility, but what happens when the size of that hydrocarbon tail increases, right? Then solubility in hexane. You have to, memorize these numbers, okay? What you've got to be able to do is compare two alcohols in a solvent, let's say, and be able to evaluate which one's going to be more soluble and which one is going to be less soluble. Somebody says, Violet says, they look like caterpillars, these ones here, these models. These are called space-filling models. So what you see here in the methanol, what it's showing here is you have the carbon and you've got the 3 hydrogens. Those are the blue spheres. And then you have an oxygen and it's got a hydrogen like that. Okay, so that's what they're showing here. And the reason that space filling models are handy is in the name, it kind of shows you how much room the atoms take up. That's kind of what's going on there. All right. Well, after all that, me yammering on, let's take a look at some problems like I promised, where we have to evaluate, looking at solutes and evaluating their solubility in a given solvent. Okay, so let's start with A, and this would make a great question on your final exam. These would be great questions. It says, predict which solvent will dissolve more of the given solute. Okay, I got sodium, methanol, or 1-propanol. Okay, sodium chloride in methanol or 1-propanol. Well, let me move ahead here where I've got a little bit more room. So we've got sodium chloride. Sodium chloride is an ionic compound, right? NaCl is made up of a sodium cation and a chloride anion. So it's got an ions, right? So we're going to have an ion. And then what kind of forces in methanol and propanol are most like the forces in sodium chloride? Well, if I look at the structure CH3OH, right, and CH3, CH2, CH2, OH, I should try to be consistent here. So I have OH. Well, what do we know about when we have an OH, right? We've got a dipole, right? So the forces here are going to be ion dipole forces. Well, which one of these molecules, methanol, in which one of these molecules, methanol or propanol, 1-propanol, is the dipole going to be more significant? Could anybody tell me? Which one of these would sodium chloride be more soluble in? Yeah, everybody's right. It's methanol, CH3OH. Exactly. So we'll put here hydrocarbon tail of 1-propanol is larger, and it's not going to interact with the ions. So there you go. So we'll say it's going to interact or dissolve best with methanol. Let's try the next one. B, we have ethylene glycol and hexane or water. If we look at the structure of ethylene glycol, it's this, okay? And then we have hexane. So this is ethylene glycol. Everybody knows what water is, so I'll draw that first. So this is water. And then we've got hexane. So hexane, I'll just write the molecular formula, which is C6H14. Okay, well, what kind of forces are we going to have with our ethylene glycol that would cause it to mix with water? We're going to have hydrogen bonding, right, with our ethylene glycol, and then we're also going to have hydrogen bonding here. In our hexane, we're only going to have induced dipole or London forces. I'll call it induced dipole because that's what I called it on the slide, induced dipole. Well, remember the rule, like dissolves like. Okay, that's our rule of thumb. And since ethylene glycol and water are both capable of hydrogen bonding, the ethylene glycol, which is antifreeze, is going to be most soluble in water, right? A hydrogen bonding is a stronger intermolecular force than a dipole and an induced dipole. Dipole, induced dipole. There we go. All right, well, let's take a look at the last one. What is it? It's diethyl ether in water or ethanol. This one's an interesting one because diethyl ether has this nonpolar portion, CH3, CH2, but then it's got the oxygen in it, and it's going to have a dipole in it, right? It's going to have a dipole going this way. So this is diethyl ether. Then we have water. There's our water molecule, which is capable of hydrogen bonding. And then what else do we have? We have ethanol. So CH3, CH2, OH. So this is ethanol. Well, diethyl ether has a dipole, doesn't it? It doesn't have a hydrogen for a hydrogen bond. It can participate in hydrogen bonding, but it doesn't have a hydrogen bond. Whereas water's major intermolecular force is going to be hydrogen bonding. Hydrogen bonding. Okay. And ethanol is going to have hydrogen bonding, but it's also got this nonpolar portion here, right? So it also has induced dipole. Induced dipole. And if we go back to the diethyl ether, not only does it have a dipole, but it's got these nonpolar portions here. So it's also got induced dipole. Induced dipole. And so the diethyl ether is going to be better able to interact with the ethanol, which also has a dipole. I didn't list it, but it has a dipole in it. And it also has the nonpolar portion, which is going to be able to interact with those portions there. All right. So that's the kind of thought process you want to have when you look at these kind of problems, where you're evaluating or predicting whether a solvent is going to dissolve in a given solute. Well, let's talk about energy changes in solute or solution formation. Let's think about the steps that go into making a solution. Now, if you're tired because it's 10:30 in the morning and the lecture's mostly over, we got 10 minutes left. Just take a deep breath and bear with me, because I think that this next part is pretty easy to digest. I think it's very intuitive if you just think about it for a second, but you got to have a clear mind. Well, let's think about, what are the steps that go into making a solution? Okay, now it looks like there's a lot of information on here, so let's just break it into 3 steps. First step, we have a solvent. Okay, in order for the solvent, like let's say you have some water and you're putting sodium chloride in it. Well, in order for a solution to form, the water molecules, not all of them, but some of them are going to have to separate, right? Aren't they? Because you're going to have to squeeze or put those ions in between them. So the first step for the solvent is going to be going from being aggregated or all together to being separated. Now, we know that since the water molecules are held together by intermolecular forces, it would require heat energy to do that. So the change in enthalpy for the solvent going from being aggregated to separated is going to be positive, right? Think about it. You'd have to put energy in to break water molecules apart from each other. Hydrogen bonding's strong, okay? And I'm just using water as an example. It could be hexane, right? We know that hexane molecules experience induced dipole. It would take some energy to break those apart from one another, okay? Next step, what about the solute particles? Okay, same thing, okay? If you have an ionic solid, or if you have, whatever kind of solid, if you want to make a solution, you're going to have to spread or break those particles apart, right? For them to go in a solution, they're not going to be aggregated anymore, and that's going to require some energy to break them apart. So what have we done so far? We've taken our solvent and we've broken it apart, okay? We've taken our solute and the same thing, we broke it apart. Both of those were energy requiring processes. Now remember, we're talking about making solutions here. We're not talking about things that don't dissolve. But if we make a solution, then what's going to happen is that the solvent particles are going to interact with the solution particles, and that step is going to release heat, right? Because you're going to go from not having as many intermolecular forces to them being aggregated together in the mixture, but now we're going to have all these intermolecular forces, and so heat is going to be released when you form the solution. What's the take-home message here, you guys? The take-home message is that when we take our solute and our solvent and we go from it being aggregated to being separated, that's an endothermic process, right? Both of those are endothermic processes. Whereas when we form a solution, right, we're making a solution, we're going to release some heat energy in the mixing process. So I should have been clear about that, but this is the delta H for mixing. It's going to be less than 0. We're going to release energy. So that's an exothermic process, okay? So what have I said? Breaking solute or solvent particles apart, that requires energy. Mixing releases energy. Got it summarized over here. If I want to calculate the overall heat of solution, how much heat is released or absorbed through the process of making a solution, I'm going to have to tally up all three of those, right? I'm going to have to tally up the delta H of the solvent and the solute, and then the delta H of mixing as well. Now remember, though, that the delta H of the solvent and the solute, both of those were positive, weren't they? Right? Both of those were endothermic processes, whereas the delta H of mixing was negative, right? Because that's an exothermic process. And so if we look at the overall process, the overall solution process can be either endothermic or exothermic. It's going to depend on the magnitude of both of these values here, okay? Now, I'm kind of considering these two as one, right? But it's going to depend on the magnitude of the delta H's. In an exothermic process, the delta H of solution is going to be less than 0, right? It's going to be a negative number because the sum of the endothermic processes, the solute and the solvent, delta H is going to be less than the exothermic term. And then when I get an endothermic solution, so if the delta H is greater than 0, it's going to be because the sum of the endothermic process, the delta H of solute and delta H of solvent, are larger, or this term is bigger than the negative term. Okay, I mean, anybody here could tell you that. Okay, you don't even have to know anything about chemistry to figure that part out. Okay, but what's the take-home message from this slide is that whether this is exothermic or endothermic is going to depend on the order or the magnitude of the endothermic processes, delta H solvent and delta H solute, and the exothermic process, the delta H of mixing. Well, let's look at some enthalpy diagrams for the formation of some ionic solutions. Where was I? Okay, so on the top we have exothermic solution, and on the bottom we have an endothermic solution. Let's just walk through it and then we'll call it a day for now. Okay, so top part of the slide right here. Here I have my solvent, right? We know it's going to take some heat energy to break those apart, so we go from aggregated to separated. Beautiful. Same thing applies for my solute. I'm going to go from aggregated to separated. That's going to require some energy. If I tally both of those gray arrows up, so this gray arrow that I have in red and this one here, I tally them both and I get this big one here. Then if I look at the change in enthalpy for the mixing process, you can see that it's exothermic, going the opposite direction, and it's bigger. Okay, so heat is going to be released. And so if you're in this kind of situation, heat would be released, and when you have an exothermic solution being formed, heat will be released, and so it's going to feel warm, right? If you were to make it and shake it with your hand, for example. In an endothermic solution forming process, we have the delta H of the solvent, delta H of the solute, solvent and solute, and we tally both of these up. But then when we mix, we only release a smaller amount of heat. And so overall, the delta H of the solution is going to be greater than 0. And so if you were to mix up a solution that is an endothermic solution, and you were to shake it with your hand, and we'll look at some examples of this in the next class, in that case, it would feel cold, right? Because the heat would be taken from your hand. Now, why don't we look at that at the very beginning of our next lecture? So something to look forward to.